So before starting this, I think we should go over the definition of the transition probability matrix. So it has entries of this form, and the value pij. So for instance, this is p00, this is p01, p02, etc., represents the probability that the process will, when in state I, next make a transition into state j. So, for instance, here, going from 0 to 1 has a probability of 0.5. And we have here that a state is transient if starting from I there's a non-zero probability that the chain will never return to I, and that it is recurrent otherwise. For solving these kinds of problems, I think the best way to do it is to draw a diagram with arrows pointing from each state to another, if there is a connection like this one. So that is what we are going to do. So our drawing is basically going to take the form of a directed graph. We'll denote 3 vertices. So we'll have 0. I'd rather do 1, but that's what this says. Then we'll have 1 here. Then we'll have 2 here. So we consider 0. It cannot go back to itself because there's a 0 probability. It can, however, go to 1 with a 1/2 probability. And it can also go to 2 with a 1/2 probability. Then 1 can go back to 0 at a probability of 0.5. It cannot go back to itself, but it can go to 2 at a probability of 0.5. And then we have 2. It can go to 0 here, and it can go to 1. However, it cannot go back to itself. This is a pretty symmetric digraph, and it's pretty clear to see here that no matter what, if it leaves a state, there will always be a chance it comes back. And over the long run, it is guaranteed to come back. So in this chain here, we just have the recurrent class. We'll use set theory notation here. 0, 1, 2. Now we are going to attempt this with a slightly more interesting matrix. Once again, we will write out our nodes, 0 corresponding to here, 1 corresponding to here, 2 corresponding to this one, and 3 corresponding to this one. So we'll first start out here. It has no chance of going to 0, it has no chance of going to 1, I should write that out as 3, and it has no chance of going to 2. It has an 100% chance of going to 3. Similarly, we can see that 1 has the same characteristic. Now we can look at 2. 2 has a probability of 0.5 to go to 0 and has a probability of 0.5 to go to 1 and no probability to return to itself or go to 3. And then finally we have 3, which is guaranteed to go to 2. Even though this is a little more interesting than the previous example, we can see that no matter what, there's always a directed path from any node to any other node. So we can say that there's only one class, the recurrent class, consisting of every node. So 1, 2, or 0, 1, 2, and 3. Okay, so now we have a larger matrix in our drawing. There's going to be 4 distinct vertices. We'll do 0, 1, 2, and then we'll do 3 and 4 here. This is 0, this is 1, this is 2, this is 3, this is 4. So we start with 0. It has a probability of 0.5 to return to itself, and it has a probability of 0.5 to go to node number 2. Now 1 has a probability of 1 over 4 to go to 0, probability of 1 over 2 to go back to itself, and a probability of 1 over 4 to go to 2. Now 2 has a probability of 1 over 2 to go to 0, and a probability of 1 over 2 to go back to itself. Now, as we can see here, 3 and 4 are not going to have any access to 0, 1, or 2, so we can note that 3 has a probability of 1 over 2 to go back to itself, and 3 has a probability of 1 over 2 to go to 4. And similarly, 4 has a probability of 1 over 2 to go to 3, and 4 has a probability of 1 over 2 to go back to itself. So it's pretty clear here that 3 and 4 are recurrent classes because 3 can go back. If 3 leaves, it's going to 4, which will always be able to go back to 3 and vice versa. So we can just write that down as our first recurrent class. However, we can look at 1 here, and we can see that 1 can go back to itself, but if 1 goes to 0 or 2, there is no directed path that will return to it. Therefore, 1 is transient. Now we can see 0 and 2, they both will, it's like the same thing as 3 and 4 here, except 1 can kind of join on to them. But we can see here that if state 0 is left, it will go to 2, and there's always a chance, because the probability here is not 0, that 2 can go back to 0. So we can note that 2 and 0 is another recurrent class. Final example we're going to do in this video. It is another matrix with 5 rows. So we'll do the same thing. We'll write out 0, 1, 2, 3, 4. So we'll start with 0. There's a probability of 1 over 4 that it will return to itself, and there's a probability of 3 over 4 that it will go to 1. And now we have 1. There's a probability of 1 over 2 that it will go to 0, and a probability of 1 over 2 that it will return to itself. Next up, we have 2. 2 has only one thing. It has an 100% chance that it'll go back to itself. Now, 3 has a probability of a 1 over 3 of going to 2, and a probability of 2 over 3 of going back to itself. Now 4 is guaranteed to go to 0. We'll first start by considering the recurrent classes. Now it's easy to see here that 0 and 1 are only going to each other, and they don't have an 100% chance of staying in their own state. So no matter what, these two, if they leave, will always have a chance to go back to each other. So we can start off with 0 and a 1 as a recurrent class. Now 2, anytime it leaves, it is going back to itself. It is not going to any other node. So we can also consider 2 to be a recurrent class. However, if we look at 3 and 4, 4, when it leaves, it goes to 0, and there is no directed path back to it. So 4 will be a transient class, and 3, when it leaves, it goes to 2, and there is no directed path back to it. So we can note that 3 is also a transient class, and we have now completed this problem.